Okay, the second new thing, a little pun in here that you'll see as we work through this. What we just talked about is maybe your applied force is on a funny angle as you push something horizontally across the ground. The next new thing in grade 12 is maybe the ground's on a funny angle, or maybe your object is on an incline, or maybe your object is on a ramp. It's going to be repetitive. I'm going to talk you through this in the solutions to those three questions, but I'll talk you through it here to try and give you a double whammy. If we've got an object on an inclined plane, so kind of boring, I'll just put like a box on our inclined plane. It's got a particular mass. If we just got a block sitting on an inclined plane, we can't get away from gravity, so there's going to be the force of gravity pulling it straight down. I'm going to call that Fg for gravity. We can't get away from normal force, so there's going to be a normal force this way. You can see as we work through it, the first question doesn't have any friction. Then I add friction. Then I add an applied force and friction. So they kind of progress. You work through those three questions, you'll see the progression, and there's a reason why I'm progressing that way. For this first one, let's say that the block is going to slide downhill. If the block slides downhill, there'd be a force of friction that's backward uphill. Friction always opposes the motion. So if it's sliding downhill, friction is going to be uphill. If that's what was going on, that's what the free body diagram would look like. What I was trying to say in the last video is whatever direction an object is accelerating, if there's vectors on a funny angle, we need to find the components of those vectors. So in this case, I'm going to switch colors. The object is accelerating down the hill. So this isn't, that red arrow isn't a new force. I'm just trying to say that's the direction of the acceleration. I won't always draw that. That's just to sort of help us get thinking. It's accelerating in the plane of the hill. It's accelerating down the hill. Normal force compared to that is already perpendicular. So I don't need to worry about components of normal force. It's already perpendicular. The friction force is kind of parallel to the acceleration. It just happens to be uphill when the acceleration is downhill. So I don't have to worry about components of the friction force. But gravity's on a funny angle. Gravity's on a funny angle compared to the acceleration. I'm always going to shoot it this way. Gravity, I need to find the components of. So I'm going to shoot this component. That's the component of gravity. That is perpendicular. So I'm going to use a little math sign for perpendicular. That's the component of gravity that's perpendicular to the incline. And then there's another component down here. That's the component of gravity that's parallel to the incline. I'm taking the components of gravity that are perpendicular and parallel to the incline because that's the direction the object is accelerating. When we start to do math, the 90-degree is down there. Gravity is the hypotenuse. Fg perpendicular is perpendicular to the incline. Fg parallel is parallel to the incline. In the videos, there's a cool little, no one always likes geometry, but if this is angle x, then the same angle x shows up in the triangle there. I think in the solution to the first one, I kind of talk you through the geometry of that. I'll let you mathematicians puzzle your brain around it in this video or watch the next one, you'll see it there. That's the free body diagram for an object sliding down an incline with friction. As you can hopefully see, this is no longer a boring case. The normal doesn't exactly equal gravity. Instead of setting this into vertical and horizontal, I'm going to look at the components that are perpendicular to the incline, perpendicular, and then the objects that are the forces that are parallel to the incline. In the perpendicular, we've got two things going on. The normal force is kind of what I would call my upward force. It's upward perpendicular to the incline. That's got to balance out Fg perpendicular. Fg perpendicular is the component of gravity that's keeping it stuck to the ramp. The normal force is the reaction to that. From a little bit of trig, Fg perpendicular, since it's adjacent to the angle, that's a cosine relationship, so katoa. So it's the hypotenuse multiplied by the cosine of the angle. The hypotenuse is gravity, that's always mg. So it's mg multiplied by the cosine. Oops, that's a little bit messy. It's mg multiplied by the cosine of the angle. That's the normal force for an object on an incline. If we cared about the parallel, well, we will eventually care about the parallel. You'd set up F net equals MA. The FG parallel is opposite that angle. That's a sine relationship, so FG parallel is going to be FG sine of x. FG is just gravity, so that's mg sine of x. So as you start working through objects on inclines, the new thing is going to be you have to take components of the gravity force. The gravity force is doing two things. It's keeping the object stuck to the ramp, and it's accelerating the object down the incline. Since gravity's on a funny angle compared to the acceleration, we have to take the components of gravity. One component of gravity, what I'm going to call Fg perpendicular, it balances out the normal force. It triggers the normal force. The normal force is a reaction to Fg perpendicular, and the downhill component is caused by that opposite side of the triangle, so it's an mg sine. That's where I'll call it quits there. Try those 3 problems, finish the worksheet, and a check-in related to inclines.